Okay, sample problem 16.4 is still determining a reaction order problem, but it's using molecular scenes. And you guys know that I love molecular scenes because I think it's a great way to make sure that we understand what's going on conceptually without getting bogged down by chemical equations and all kinds of stuff that can complicate things. So, at a particular temperature and volume, and again, this is going to become important as we move on later and understand that there's a temperature dependence of rate constants. So if we're looking at methods of initial rates and so forth, it's really important that we stay at the same working temperature to gather this data. So at a particular temperature and volume, we've got two gases, A and B, reacting. And we can remember what's going on here, that the B is blue. So the following molecular scenes represent starting mixtures for 4 different experiments. So this again is not unlike some of the other sample problems that we've done, or the in-class problems that we've done, where we're given a table of data. What we really have here though is we're given this data in pictorial form. So we've got 4 reactions. We've gotten, they've given us rates for 3 of these 4 reactions. And again, they've used pictures to represent concentrations rather than actually giving us concentrations. So we're going to treat this problem exactly the same, but we're going to get concentrations by inferring what we see from the number of molecules. So again, the reaction order with respect to A. So A is our red molecules. So if we want to figure out what the reaction order is with respect to A, what we need to do is find another reaction that has the same amount of our blue, because if we're figuring out the reaction order with respect to A, we need to find out how does the reaction rate get changed when we change the concentration of the red species, but again, not changing the concentration of the blue species. So to figure out the reaction order with respect to A, we need to find 2 molecular scenes that have the same number of blue spheres. So again, we can compare 1 and 2. We can see going from 1 to 2, we have doubled the concentration of red. So again, to answer part A, we want to compare 1 versus 2, because that will hold the concentration of B the same, B being the blue spheres. And we'll see that we will have a 2-fold increase in the concentration of A. And we have to compare and see what happens in terms of rate. And looking at this, and again, the math is fairly easy, we can do this in our head here, we can see that we have a 2-fold increase in the rate. So when you double the concentration and the rate doubles as well, we can take that to mean first order. So that gives us first order with respect to A. So if we want to figure out with respect to B, that means we have to find 2 molecular scenes where the number of blue spheres is changing, but we're keeping the number of red spheres the same. So again, there's a number that you could choose for this. I'm going to choose to compare 1 versus 3. But to just show you again, if I wanted to have 2 that I could compare 2 versus 4. But again, the problem here is that we don't know that reaction rate. So comparing 1 versus 3, okay, we can see going from 1 to 3, I'm keeping the concentration of A the same, and I'm doubling the concentration of B. So we have a 2-fold increase in the concentration of B. And if we compare what happens with the rates here, we can see that there's a 4-fold increase in the rate. And again, that means that we are second order with respect to B. And adding these 2 together, that means we are third order overall. So exact same treatment of data as we had with our original problems, but we're inferring concentration information from what we have here in our molecular scenes. Okay, second part here says to write the rate law for the reaction. The generic form of the rate law would have been rate equals rate constant times the concentration of A to the m power times the concentration of B to the n power. But part A actually allowed us to figure out what these reaction orders are. We figured out that it's first order with respect to A, so that means that that's going to be a 1. Second order with respect to B, so that's going to be a 2. So the rate law is rate equals rate constant times the concentration of A to the first power times the concentration of B to the second power. Okay, the last piece of information here asks us to predict the initial rate for experiment 4. So again, looking at, now that we know what the reaction orders are, there's a number of experiments that we could actually compare. I'm going to choose to compare 3 versus 4. So again, if we look at comparing 3 versus 4, we've kept the concentration of B the same, but we've doubled the concentration of A. We know that it's first order with respect to A, so we would expect the rate to increase twofold because the concentration of A increased twofold. And again, this we get from it being first order with respect to A. So again, doubling this tells us that the rate should be equal to 4.0 times 10 to the minus 4th molar per second. And notice you can write molar per second, which is the same as mole per liter second. So a couple of questions that people have kind of asked to just kind of highlight as we have this last problem as we finish the method of initial rates. When you're comparing things, I tend to like to compare whole numbers versus fractions. So when you're comparing 1 to 2, you could just as easily say compare 2 to 1 and say we have half the concentration of A here, and the reaction rate was halved. But again, working with fractions is a little bit more complicated, I think, to work with. Two reactions that we can't compare early on, right, are reactions 2 to 3. We really can't figure out what's going on here comparing 2 to 3 because we're changing two things at once. Going and comparing 2 to 3, we're actually decreasing the concentration of A and doubling the concentration of B. What we actually see here is the reaction rate actually gets faster, even though we've decreased the concentration of one of the species. And that has to do with the fact that it's first order with respect to one and second order with respect to the other.